Today I'm going to walk through how to set up your first project in MPLABX using assembly language and the MPLABX compiler. It was a little convoluted, so I figured I'd show you that, and then I'll walk you through some code that I did so that you can have a row of LEDs maybe blinking back and forth in a kind of chase pattern, if you will. So first you'll open MPLABX. If you don't have it, you can download it from microchip.com/MPLABX. Now the first thing you'll do is create a new project. You can do it here, you can do it from the file drop down menu, or you can just click the plus folder. You'll do a standalone project, click next. You can go through all of the Microchip PICs they have, or you can narrow it down. I'll be using the 18F45K20, so it would be the advanced 8 bits, but I'll just do recently used, and it's already got it selected. Then you'll select your hardware. I'm using the PIC 3. Then you'll select your compiler. I'm not using a C language, so I haven't downloaded any of the C compilers, but you can get those, the standard for free, I believe, and the Pro you have to pay for. So I'll just use the MPASM, or I call it MPASM. Click next and give it a project name. We'll just say sample project. Click enter or finish. And it opens up here. So the first thing you want to do is add your linker file. You right click, add existing item. You'll have to find it, browse to your main folder. Your main disk, I should say, and then your program files, Microchip, MPLABX, MPASMX, and then your linker file will be here and the linker folder. I'm going to just type mine in because it takes longer to search for it. And select, and then you'll see if I expand that folder there, it's added it. You see the source files doesn't have anything in it, so we can right click. Now we can add a new empty file, or we can add an existing item. If you add an empty file, then whatever you name it, say you call it new file, I usually call it whatever the project is, you have to type the .asm extension on it. Otherwise it's just a blank document kind of file and it won't read it, the compiler won't read it. But I'll show you really quick, even though that's how I do it. If you're new and you want to kind of let Microchip do some of the setup for you, you can add existing item, go up a folder back into the MPASM, and go to templates. And you can use a code or an object. You can read the difference in the README. I'll just select code, and we'll look for 18F45K20, 18F45K20, and then it adds it. You can double click it, and it will open it here. Okay, so if you decide to go this route, then basically Microchip has kind of populated a lot of the setup work for you. You'll see they give you a basic code template, and they call out your list and your include file, and then they'll set up some of the oscillators and watchdog timers and stuff like that. You will have to read up in your data sheet about this, but I've found even through the data sheet it can be hard to find certain things like, how to turn a watchdog timer on and off. Some PICs use just WDT, and some use WDT-EN for watchdog timer enable. But it is all in the data sheet if you search enough. And then they just kind of set up some variables for you, which are basically definitions. Basically what this does is C block calls out to set up multiple definitions at once, really, or variables I should say, and they assigned it this hex address, so it's register 60, which is just a general purpose register, and the first variable will go to 60, the next variable will go to 61, the next to 62, and so on until you issue the nc command. So again, here's some stuff where they initialize the EEPROM and the reset vector, basically telling it on reset, go to the beginning of the code, which is going to be 000. And you know, so the high priority interrupt service and all of that. So it could be a good place for you to start if you want to learn a little bit about setting up and configuring. But I didn't do that. I just started with a scratch one. And so what we'll do is we'll go ahead and close this sample project. And we'll open mine. And you can see I've already got the linker file. And then here's the ASM file that I created. So you can see that I do a very similar thing. I start with a title and a date and my name and a description. And then I do some basic configuration where I list the PIC that I'm using and make sure to tell it to include that file. I kind of like to use all lowercase because Microchip changed the way that the compilers read things based on some bugs they were having with Linux, I believe. So if you have capitalized file names, it'll give you a little warning, even though it really isn't a big deal. So anyway, so the first thing I do is configure my oscillator, and what I've done is told it that I want to use the high frequency internal oscillator with IO on RA7. What this does, if I put 7.6 here, then it'll give me IOs on RA6 and RA7, but I want to use RA6 as a divide by 4 frequency output. So whatever I set my internal oscillator to, the output present on pin RA6 is going to be 1/4 of that frequency. And that's just, I like to do that so I can look at it with the scope and verify that it is the right frequency. And then everything's set up right. And then here I've disabled the watchdog timer, which isn't necessary, but this is a kind of a program that's just going to loop. So if we want to use the watchdog timer, then we'd have to write in the program somewhere to keep clearing it. Otherwise, it would time out basically, and it could cause some issues. And then I've disabled the analog inputs for port B. Didn't really have to, but you know, why not? I'm not using them. Same thing with the master clear function. I've disabled that, and I didn't need to, but if you do choose to disable that on the 18F anyway, then you can use that master clear pin as an additional input. I believe it's an analog input. I don't know why some of these lost their color. So then I disabled low voltage programming and disabled the debug feature. Again, don't really need either of those. Probably don't need to disable them, but you know, not a big deal. So the next thing I did was set up some initial definitions, and you can see like right here, if I keep skip in column 1, it'll give me an error later. So I have it in column 2. And then this is the C block that I talked about earlier, where it sets up this timer 0 count to hex address 0x020, which is just again a general purpose register. And basically I'm going to use that as an overflow for the interrupt count for timer 0. And then I've ended it. And I just did it like this so you could see the two different ways of setting up, defining a variable. I could have just as easily wrote timer 0 count equals 0 by 020, and it would do the same thing. So the next thing I'll do is tell it where to go next. And I want to do an initialize section where I'll set up some initial parameters for the program, and then after that I won't go back there. And so I've just made a label in the program called initialize and told it to go there and just start the program at hex address 0. It's good enough. It's, you know, it's not a very complicated program, so I don't need to use 0 for something else. Really, I probably don't even need to define that and just let it run wherever it wants, but it's good practice, I guess. And then the next thing I do is set up the high priority interrupt service routine at hex address 8, which if you look at the data sheet for my particular PIC, you will see that the high priority interrupt vector is at hex address 8 and the low priority is at hex address 18. So that's why I've done that. Now, I'm pretty sure that this is all set up in the include file that we specified at the beginning, but I put it here. Helps keep organized and looks nice. Helps me keep from assigning that register to something else. So I've just named it HPINT as the label. But we don't actually do anything here, because when we get to this line of code, we go to initialize. So that's where we'll go. We'll skip the interrupt routine for now and go down here. And you can see it's just some initial configuring. And the first thing I do is configure the oscillator. Yes, I told it that I want to use the internal oscillator in the beginning of the program, but now I have to actually set it up and tell it how I want to use it. So if I pull up my data sheet and go to the oscillator module, I have set it up. All these bits are zeros by default, so all I've done is set the 3 IRCF bits 6 through 4, and I've set them all. So I've set it to a 16 megahertz frequency, and I've left this clear so the device is running from the internal oscillator, and I've set the IOFS, the frequency stable bit, so that the frequency is stable. And I left bits 1 and 0 clear, which means the primary clock is determined by config 1H FOSC, bits 3 through 0. So anyway, next thing I do is clear ports A and D. So I clear them so there's nothing on the pins. Then I clear the lat registers of each port, and what that does is that's actually writing to the port itself and not just the pins. You have to Google and read the data sheet to see the difference between writing to a port and a lat register. But basically, anything you write to a port is what's going to be at the pin or on the pin, and anything that you write to the lat register is actually setting the port to that value. So you can actually have a 0 and a 1. If you read the lat register, you might get a 0, but if you read the port, you'll get a 1 for that particular bit. So, and then I've cleared the tri-states D and A, or tris A and tris D, however you want to say it. I've cleared those registers to set them up for outputs. Next thing I do is enable the priority levels and the high priority interrupts. And again, from the data sheet, you can see how to set that up. And if we go to interrupts, you can see for my particular PIC, I've got a bunch of different registers and everything, but you can see I found the global interrupt enable bit here, and since I'm going to set the interrupt priority enable bit, then when I set that to a 1, this bit here, bit 7, I set that to a 1, it enables all high priority interrupts. Well, the IPIN bit isn't in this register. It's actually in the Archon register, I believe. So you got to do quite a bit of searching to find this stuff. So here's the PIR register, and then there's the PIE register, and eventually you'll find the Archon register, and you'll see that that's where the interrupt priority enable bit is. So then I clear the interrupt flag and enable the interrupt. Again, from the data sheet, we were just at the intcon register there, and we want to clear it first before we enable it. That way, if it happens to be high, it won't interrupt our initial settings configuring and go to the interrupt service routine where we'll never get to finish this. Then I'm going to load a value into the timer 0 count register that we defined earlier. This is an arbitrary value. It will set up the period, so it'll be slower if it's bigger, faster if it's smaller. And so I just move it to the working register and then move that value to the timer 0 register, or the count register that we defined. And then we're going to configure enable timer 0. Again, we'll move the value to the working register and then move it to the timer 0 control register. And if we look at timer 0 module, timer 0 control, I have set it up to C7, so a 1 here enables timer 0, a 1 here configures it as an 8-bit timer, and then a 0 here says to clock off the internal instruction cycle, and a 0 here says increment on a low to high transition. A 0 at the next bit says the prescaler is assigned, and then the last 3 ones, which is the 7, says that I'm going to use a 1 of 256 prescaler. And then I'm going to set RD0 on port D high, so that's going to illuminate the first LED and allow the program to start operating properly, where it'll chase the LEDs back and forth. So you might ask, why don't I just put that in the main program? And you can try that, but what happens then is every time it returns to the main program, it says set that bit high, and so that LED stays lit up the whole time because everything happens so fast. It sits here, it's lit up, it gets an interrupt, it comes up here, it does its routine, comes back to the main program and says, well, it needs to still be lit up. And well, if it's lit up all the time, every time it comes back there, if it's lit up, then it basically just stays lit up, and that's not really what we want it to do. So you'll see that the program will just loop here continuously until an interrupt is received. And then once that interrupt is completed, the program returns back to the main section here and waits for the next interrupt. So it just loops back and forth between here and here, because it always goes back to main while it's waiting for the interrupt, and it never gets to end where it says bye-bye. So now let's look at the high priority interrupt routine. So this is the label that we defined at hex address 8, and the first thing we do is test the interrupt flag of the interrupt control register and see if it's set. If it's set, then we go ahead and we move to the if set label. Otherwise, we skip that command if it's clear, bit test port intcon skip if clear. So we test this bit of the interrupt control register, and if it's clear, we return from the instruction, from the interrupt basically, and we go back to main and we wait for the next interrupt. So if it's set, then we decrement the timer 0 count, and we'll keep doing that until it gets to 0. which it should get there pretty quick since we only loaded it with a value of 1. So it's going to test that port until that port is 0. Once it's 0, it moves on. If it's not 0, it goes to interrupt flag repeat. And the interrupt flag repeat just says clear the interrupt flag and return from the interrupt. So then we get another interrupt and it comes back up here, test it, and until we get it clear, which like I said will be quick. So once it's clear, we basically reset the timer counter register with the value that we chose, which happened to be 1. So once we've done that, then we come here and we do some bit testing. And if the bit is set, this bit of the skip register that we defined up here, if the first bit of that register is set, then we'll skip this command. And that'll basically allow us to start rotating back to the right. But if it's not set, if it's clear, then we're going to rotate to the left. So we're going to rotate from 0 to 7. And so after this command, let's assume that this isn't set yet, because it's not. We rotate to the left. So that means RD0 becomes 0 and RD1 becomes a 1. So now RD1 is the only LED that's illuminated. Then we'll test the carry flag of the status register. And if that's clear, then we'll skip the next command, which tells us to set that skip bit, which will allow us to rotate back to the right. So if we skip that command, then we test it again, and it's going to still be clear because we haven't set it up here. So if we skip this command, which is the rotate right command, then we test port DRD0, which we have just rotated to the left. So now RD0 is a 0, and so it'll skip this command where it'll tell it to clear it. So we're going to continue, basically we're going to continue in that fashion until we get all the way into the carry flag. Once we get the carry flag set, we're going to start rotating back to the right. So what happens? We tested here and we said, oh, well, it's still a 0, so we're going to rotate to the left. Let's assume we're at RD7 is high right now, and we rotate to the left. Well, that's going to set the status flag. So now we're going to test that. It's not going to be clear. So we're going to do the next command, which will set bit 0 of the skip register to a 1. Once that becomes a 1, we test it again. It's a 1 because we just made it a 1. So then we'll start rotating back to the right. And then we'll test port RD0 and see if that's set. If it's set, then we'll clear the skip register. But it's not going to be set yet until we rotate through all of the other bits, basically from the carry flag back to RD1. And then once we get to RD1 and we rotate to the right, then we'll see, oh, okay, RD0 set, so let's clear the skip bit. That way, next time we come back through this routine, we start rotating to the left. So once you've got your file complete, your ASM file complete, and you've got your linker file, then you can do the hammer and broom, which is a clean and build, and you can see if there's anything wrong with your code. So I'm going to move this definition into the first column and hit the broom and hammer, and we'll see what happens. So you see it cleans, and then it goes and clean successful and build successful. So that's nice. Usually it'll give you a warning there, and it'll say, hey, we found a definition in the first column, you know, move it. And so let's see, let's go back here and move over. Let's delete it and see if it works that way. Otherwise, I'm not going to spend too much time on this trying to show you. Yeah, well, I won't do it now. Anyway, usually it'll give you a link if you've got some problems here, and you can click that link and it'll take you to that point in your code where the issue is. Usually it'll say, you know, label found in first column or something like that, or definition in first column, you know. So if you do that, then you can go back. Now, if you've got a simple thing like that, it's just a warning, you can usually compile and load your project and everything's fine. But if it's a serious issue, it won't let you make your project and load it onto the PIC that you're using. So now, just like one other little thing I want to show you is if you're using the PIC at 3 and you need to power your circuit from the PIC at 3 instead of from an external power supply, you can go into Project Properties and select the PIC at 3. I don't know if this is the same for other programmers, but for this one, this is how it works. Drop down here on the option categories and go to Power, and you can highlight the power target circuit from PIC at 3 and apply it. So if you're having problems getting power to your circuit from an external source, then you can try doing that, and that might help. Other than that, once you're done, you've cleaned and built it, and it's successful, then all you need to do is click Make and Program Device, which is the down arrow. You can see there's a couple different things you can do. You can load the program onto the PIC at 3 and then just power the PIC at 3 externally and use that to program a circuit that's away from the computer or something like that. You can program it for debugging, or you can make and program the device, which is the first option that I've always used. And then here, if you've got a PIC that, you know, maybe you lost the hex file for or something, and you need to get the code off of it, you can read the device memory and save it to a file, or, you know, you can read the data memory as well and save it to a file. So that could be useful. I haven't had to use it yet, but anyway, that's how you program the PIC. So that's it in a nutshell. I'm going to send you to the video now where you can see it in operation. Please feel free to comment, like it, hate it, subscribe, don't subscribe, ask questions, and I hope this has helped a little bit. I know it was difficult for me, really just getting set up, finding all the files and stuff like that, and how to get this up and going. But you know, that's what the internet is for, and I did a lot of Google searches for my particular PIC. So if you're not using an 18F45K20, please make sure to double check your data sheet, because these registers aren't always going to be the same. You'll have to do some manipulating. But again, I hope you enjoyed it, and I hope it's helped. And here is the main video. Okay, so now we'll go ahead and do the demonstration part of this video. This is my little lab bench, and here's my little demo board. As you can see, I just have it set up to 2D batteries, and I just plug it in, and you'll see these LEDs start going back and forth. And there you go. Just chasing each other back and forth. And if I probe RA6 over here, as we were talking about earlier, you can see, well, I don't know if you can see, but that is a period of 4 megahertz, or frequency I should say, not really the period. Anyway, back down to the board here. As a little bonus, if you watch my next video, I will teach you how to make it do this. So whenever it receives an interrupt from the switch, it just flashes them all on and off. And I've got that code written, but I don't like it. It's kind of ugly and laborious, and I want to refine it and make it a little better. But once I do that and get it operating in a different manner, then I will upload that video, and you should be able to just modify this code just a little bit to add that interrupt into it. So thank you very much.